Hello everyone. Hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today, we will go through the core concepts entitled as the demarcation of catchment area and command area. Basically, the GIS and remote sensing concepts we are learned to a vital civil engineering tasks that are for planning of water resources. So we will explore how GIS is used to demarcate two critical zones of any dam project, the catchment area, which provides the water, which stores the water, and the command area, which receives that stored water. By using digital elevation model and satellite imagery, we can replace traditional topographic surveys with rapid, accurate digital modeling. So GIS helps in detailing, delineating catchment and command areas of a dam, where this catchment area or this GIS is useful to manage the water resources efficiently. Under the principle where digital elevation model and hydrological analysis tools comparatively work for the same. So the accurate boundary mapping and flow analysis are the characteristics for that. The planning, the irrigation and the flood control system, planning, irrigation and the flood control system are the applications of that GIS which is used for the demarcation of the catchment area or the utilization of the command area, which supports the sustainable water management. So the fundamental hydrological unit is the catchment area, where water is the source which is stored with respect to the topography which is available based on the terrain. So the schematic concept is that we have to collect the overall rainfall at the area with respect to the slope available naturally, that are called as the drainage basins. So rainfall into basin with respect to divided by the ridge line, and that whole ridge lines divide the total rainfall inward and outward. So real world example is that if we have to mark the wall of the dam location or site selection for the dam, then we have to be aware about the ridge lines. So the area for which rainfall flows into a river or any type of lake or any type of reservoir where catchment area will be marked. So the ridge line is nothing but the topographic divide connecting high elevation points. Water flows perpendicular to the contours, moving away from that ridge line. The patterns, hard rock terrain often creates the tree-like drainage patterns, indicating high runoff potential. So if we have a large amount of slope, then we get large amount of water in a minimum time. So our catchment area will be full in minimum duration. Moving towards the watershed and delineation watershed concept. The basic goal behind that watershed delineation is that converting the physical topography into digital boundaries. So we have to convert the existing natural topography into a number of digital boundaries based on that GIS, based on that GPS, where positioning is there. The logic behind that delineation procedure is we have to identify the drainage divide lines or basically ridge lines, so that in GIS, this is automated by identifying the highest elevation points that enclose the drainage network, where the topography or we can say that terrain is most important for the connectivity, or it will play the key role for the connecting the two or more ridge lines. The network is a series of interconnecting lines where flow moves from source nodes to junction nodes. There are two types of nodes, source nodes and junction nodes. So the network is a series of interconnecting the lines where flow moves from source nodes to the junction nodes. So step one, raw contour lines. Step two, digital overlay, where pour point is marked based on that drainage, or we can say that the river path. And step three is the watershed polygon. So the catchment area or a watershed is the geographical area from which all rainfall drains toward a common point are flowing. In our case, if we have to construct the dam site or if we have to locate the dam site, then we can use that watershed area. For any civil engineer, knowing the precise boundary of the catchment is essential for calculating the total runoff and the peak discharge in that area where the dam must have to be constructed or must have to be operated. In GIS, we define this area using topographic data identified ridge lines that acts as a drainage divides. Accurate demarcation ensures that the dam is designed with the correct storage capacity and the spillway size to prevent catastrophic failure during the heavy flood events. So, watershed delineation is the final stage of catchment demarcation by specifying that the dam axis, or we can say that the core point, the GIS software identify all upstream cells that contribute flow to the specific point. Means the whole part collect the water, converted it into flow, and that whole flow comes towards that core point. At that location, we can construct about dam wall. The output is a polygon representing the entire catchment area. As a civil engineer, you would then calculate the total area of this polygon to use a hydrological formula like the rational method to calculate the total catchment area by using planimeter also. This digital boundary is the most critical input for estimating the inflow into your reservoir and determining the long-term water availability for the project. Moving towards the topography, the most important concept is the DEM, digital elevation model. This is the 2.5 dimensional surface also. If we consider a 2D raster map, just like a grid map, where n number of rows and n number of columns are there based on the Cartesian coordinate system, x, y, z axis, and this 2D raster map is converted into 3D plane by the use of or by the sake of digital elevation model, where x, y, and z is the elevation. So the digital elevation model is a representation of terrain where elevation is the z-axis at a specific xy coordinate, where the 2.5D concept is launched because in GIS, the digital elevation model is often considered as a 2.5 because it allows only a single z value for any two xy coordinate. For any two xy coordinate, there is a single z value. That means that 2 xy and 0.5 z. So 2.5 dimensional surface. What is the utility behind that? The primary input for automated slope aspect and the flow analysis. So with respect to the terrain, the height, that elevation decides the actual flow and the actual slope so that we can collect the large amount of water in the catchment area. The foundation of catchment demarcation in GIS is the digital elevation model. The foundation of catchment demarcation in GIS is the digital elevation model. This is the raster grid where each cell represents the elevation of the ground surface. Using the digital elevation model, we can mathematically determine flow direction of water for every pixel or grid on the map. This digital approach is far superior to manual contour tracing because it accounts for suitable terrain changes that might be missed by the human eye. In today's practice, engineers use high resolution digital elevation models from satellites like SRTM or Cartosat to model complex mountains terrains with high precision level. This digital elevation model works with respect to the pre-processing and then flow direction and accumulation of the data. So before we can calculate the drainage, we must perform the digital elevation model pre-processing. So the raw digital elevation model data often contains sinks. Sinks are nothing but a small depressions or errors in the grid where water would theoretically get stuck. We use that fill tool in GIS to level these depressions, ensuring a continuous surface for hydrological modeling. Sinks are nothing but small ponds with respect to topography. So we have to use the fill tool in GIS to level their depressions on the terrain. Secondly, the flow direction and the accumulation of data. Once the digital elevation model is filled, we calculate the flow direction, which identifies the steepest downfall or steepest downhill path for each cell. From this, we generate the flow accumulation raster, which counts how many upstream cells drain into each specific cell. So high accumulation values indicate that the presence of stream channels. This allows the GIS to digitally discover the drainage network of the site. After that, we have to see the command area, the service zone, where we have to store the water in the upstream side and we have to use that water in the downstream side. So with respect to that, the catchment is the supply domain, dam wall is the barrier, and the command area is a demand domain. So supply and demand, we have to maintain the demand with respect to the available supply. So the area downstream of the dam that can be economically irrigated by the water supply system, which is the main role for that stored water, where we can achieve our command area. We move from the supply side, that is from the catchment side, to the demand side, that is the command side. So the land use maps identify arable land versus wasteland to calculate the return on investment. So the catchment is above the dam, the command area is below the dam side. That can be irrigated by the reservoir water. It is characterized or it is categorized into the cross command area, that is entire region, and the culturable command area, that is the area actually suitable for farming. Cross command area is the entire region and the culturable command area is the area actually suitable for farming. So GIS allows us to map this area by analyzing slopes and existing land use patterns. For an any irrigation engineer, demarcating the command area is about the efficiency because ensuring that the canal network or the water distribution network is designed to reach the maximum possible acre area with minimum water loss. So we have to use large amount of data. We have to use large amount of water as a data, as an input from the catchment, from the supply to the output or to the beneficiaries or to the demand area, which is also called as a command area. So if we are dealing with the irrigation intensity, then we have to check the efficiency of the distributed water with respect to the intense flow. So basically, the command area is nothing but a land use or is nothing but a land cover. We can also say that the land use land cover analysis to refine that command area. We use satellite imagery to perform the land use land cover analysis, which helps us to identify that existing forest, urban areas, rocky terrain that cannot be irrigated. So that area must have to be excluded from that premises or the total area. So in GIS, we subtract these non-culturable areas from the total area to find that the actual culturable command area. For an any engineer, the land use land cover map is essential for calculating the crop water requirement. By knowing exactly what is being grown and where that crop is growing, we can design a more precise and suitable water distribution schedule. So, with respect to that command area, the gravity is the primary driver or gravity is the primary tool. With respect to that gravity, the whole water is to be divided with respect to the slope for irrigation canals. So, slope analysis is vital for demarcating a command area. Using that, the digital elevation model, we identify areas that are lower than the reservoir level but still have enough slope to allow for natural flow. We exclude areas that are too steep for agriculture or too flat for proper drainage. So in GIS environment, we can instantly filter out that land parcels which is topographically unsuitable. It ensures that the proposed canal alignment are feasible and that the water will reach the fields without the need for expensive pumping stations. Moving towards the irrigation intensity, if we have the sufficient pumping stations, then we can maintain the efficiency with respect to measure how intensity the land is utilized. So basically, irrigation intensity is an efficiency that measures how intensively agricultural land is utilized using available irrigation water resources. An irrigation intensity greater than 100%, which indicates that multiple cropping seasons. An irrigation intensity greater than 100% indicates that multiple cropping seasons, such as Kharif, Rabi, supported by irrigation facilities. So, by using the tool of remote sensing and GIS, it will more helpful to monitor irrigated areas, cropping patterns, water resource management for optimizing canal systems, dam irrigation, planning, dividing agricultural land utilization. Moving towards the flowing water on the topography, that is called as a runoff, we have to estimate the amount of runoff. That runoff is a portion of rainfall that flows over the land surface into streams and reservoirs after accounting for infiltration and other losses. High drainage density indicates that impermeable soil. High drainage density indicates that impermeable soil and rapid runoff. So while low drainage density suggests permeable soil and better groundwater recharge. So for farming, we require that permeable soil where better groundwater recharge is available. But if we have to estimate the actual amount of runoff with respect to the catchment area, with respect to the command area, with respect to the storage of water, then we require impermeable soil so that large amount of water will be stored in that catchment only from that total watershed available. So with respect to GIS point of view, remote sensing is a tool for watershed analysis, flood prediction, drainage planning, reservoir management, and runoff estimation with respect to the water resource department or in the hydrological domain. So infiltration and its losses, then total seepage losses are also affecting the actual runoff estimation. Sediment yield estimation refers to the soil particles carried into reservoirs due to erosion. In summer season, due to the extreme heat, soil gets eroded. In the first and second rainfall, that whole eroded soil is flowing with respect to the runoff. Based on their gradient or slope, the whole water is stored in the catchment area with respect to the silt, which gradually reduces the storage capacity and lifespan of dams by filling dead storage holes. So major influencing factor include slope, steepness, lithological characteristics, or topographical characteristics, or type of rock which is available. Also, the rainfall intensity and vegetation cover which control the rate of soil erosion and sediment transport. Civil engineering point of view or GIS application point of view, remote sensing is a tool which is used to overlay the soil, slope, land use, and rainfall maps to identify erosion prone areas, support watershed management, and plan soil conservation measures such as check dams and reservoir protection works. So, with respect to that reservoir protection works, we can check that steepness, that rock type, that intensity of rainfall, and that vegetative cover to minimize the sediments which are captured at the place of catchment, which affects the actual dead storage. Reservoir planning application, which is the part where layer to layer analysis of the raster will be there. The goal is that converging evidence to find the feasible site. So basically, reservoir planning involves identifying the most feasible dam site by integrating topographic, hydrological, geological, and environmental data using the remote sensing and GIS techniques. Important factors includes that a narrow gorge to reduce dam cost, just like valley, a large catchment area for maximum water storage, stable geological conditions to prevent leakage, and the minimal displacement of settlements and ecological resources. GIS overlay analysis or the layer by layer analysis helps engineers to evaluate the catchment volume, foundation stability, land use, and displacement impacts for optimal dam axis selection or the site selection of dam wall and the suitable reservoir development. So, the reservoir planning is an application on the basis of that demarcation of catchment area and the watershed. We can use that stored water from that reservoir for various activities. We have to check the stability of dam. We have to use the stored water in the command area, and we have to maintain the safety for the life of the persons who are depending on that water by using the catchment volume and the terrain activities. Stay tuned, guys. Happy learning.